Hello and welcome everyone, this is Mr. UMath again. In today's video we want to have a look at a very interesting function and try to find its radius of convergence without having actually these guys here. So these are our ANs. We don't want to calculate these ANs because they are very complicated for some reason. Never mind, but you know what kind of function that is representing this series, and we want to find out where, or better, how large is its radius of convergence. And there is a very important theorem out of complex analysis, and this states, okay, I want to draw this, maybe it's very easy. Actually, you can only do this if you are going for complex numbers. So this is the real part x, this is the imagery part, so x plus iy, for example. Sometimes this is also called the RE of a complex number z. So let's just write it, this is the imagery part of z. Okay, and what this statement, or better theorem, tells you is to find the radius of convergence, the only thing that we have to do is we have to find the singularity that is closest to the origin. For example, a singularity or pole, okay, of the function. Now imagine we would have a singularity in here. Okay, for some reason our function here, for example, has a singularity, meaning that it just runs off to infinity. In order to find the radius of convergence, what you have to do is take the distance between the singularity and the origin, and that's actually your radius of convergence. Pretty easy. Okay, now if you have multiple points, then actually it's the singularity this is which is closest. And actually, if you have a look now, I've drawn them very stupidly. Now actually this would be the radius of convergence. Okay, if we would have many singularities, I maybe make them with stars. Okay, this is a star, this is a star, this is a star. There you see, this is the closest, and this would be the radius of convergence. So this is let's make it with such a snake sign on that. Okay, now we want to find the radius of convergence of this guy because we are too lazy. Okay, we don't know what the function looks like, we just know that the function is something like this. We don't know the Taylor series. Now in order to find these singularities, there are many methods, and in order to do that, we want to have a look. Actually, what you see is that we actually have also a singularity in x equals 0. But what is important about this is that in x equals 0, we have above and below a 0, so we could actually go ahead and do a analytic continuation. So what we are doing is actually we want to find out all the zeros of this guy here below. Okay, so let's write it down, and I will switch to, so actually to complex number z is equal to 1, and what we do is we put this guy here on the right hand side, so we get 1. Now in order to solve such an equation, we have to do a little bit of tricky stuff. First of all, we know that 1 can be written as e to the I multiplied with 0. Okay, and you see I have left here some space, plus 2 pi k. Okay, why 2 pi k? Because if you are in a complex coordinate system, sometimes called also the Gauss plane, what you can do then is this point is the same as I go around for 360 degrees, or 2 pi. So I'll come back to this. This is nothing else than the periodicity in the complex plane. So this is what we know, and from that it's pretty easy to solve because we have here e, we have here e, so the solution is z equals I0 plus 2 pi k, and remember k can be any number out of z. So what we get is actually nothing else than all the singularities are lying on 2 pi ik. Okay, now maybe I'll just draw them in. So for k equals 0, we have a singularity in here, but I told you this is a removable singularity, so not actually a problem to us. But what we have another is, so if we plug in k equals 1, so we have here on the imagery axis im of z, we have here 1, 2, and I will just label this as 2 pi. So we have here a singularity, and at the same time we have here at minus 2 pi, because if we plug in minus 1, we get this guy here. So we have here a singularity, and actually you would have here even more for 4 pi, 6 pi, and so forth, and here below also. But what you see is the closest singularities are these guys. Pull in a circle. And what is its radius? Pretty simple to see. The radius is equal to 2 pi. Okay, and from that, without even doing any ratio test or anything else, we can actually see what the radius of convergence is. This guy is converging for all numbers x, okay, and actually from their magnitude that is smaller than 2 pi. What is happening on the boundary? This is a very hot question. We actually don't know what is happening at the boundary, not for this function. We should, or better, we have to analyze it, what happens on the boundary. Sometimes you get something useful and sometimes not, so just this is the more rigor proof for us. We know that this is convergent. Okay, this is convergent in some kind, in some manner, and what is even more important for us is that we know that this guy here is converging on a radius of convergence of 2 pi, because it doesn't matter which value we plug in here, this function, or better, this Taylor series, so actually the function would be living also outside, but because of that singularity we fail to reproduce the singularity of this function in the Taylor series, because it's just a polynomial. Okay, it cannot reproduce its singularity, so the function just lives in here in this domain, and if it lives on the boundary for special values, we don't know. You must really go ahead and analyze if it's really converging, if it's really the same value. Okay, I hope this showed you a way how you can solve such problems. For example, actually you could have given a function. Okay, let's imagine you have given some function, you actually don't know anything about the function, but what you know is it has a removable singularity in here, it has a singularity here, non-removable, and then you should go ahead and say what is the radius of convergence. You would say, okay, this guy is here removable and this is not, so this is the radius of convergence. So you would just have to read it out, actually finding the singularity. And actually okay, I didn't tell you how to find this guy here. Actually let's imagine this would be let's say -1 and 2i. Okay, so this is -1 plus 2i. How do we find the magnitude of this guy? It's nothing else than the Pythagorean theorem. So we have -1 squared plus 2 squared, and if you go ahead and calculate, this is 1 plus 4, so the radius of convergence, so if these coordinates would be that, then the radius of convergence r is equal to square root of 5. Okay, without anything, you don't even know what the function looks like, but you know the radius of convergence is guaranteed to be equal to square root of 5. Okay, that actually concludes this video about singularities and the radius of convergence. I hope you had fun. If you like my videos, please give thumbs up, and I hope to publish some new videos as soon as possible. Okay, see you guys.